Greetings, mathophiles. Welcome to a video on the statistical process of hypothesis testing, which is a means of trying to determine whether or not an apparent relationship actually exists. And it can take a lot of different forms. It can involve a lot of different probability distributions. We're only going to take a look at one today. You're going to get a little more out of this video if you know the terms binomial and hypergeometric probability distribution. You don't need to know them in order to get the thrust of what we have to talk about today, but I will link a couple of videos in the description if you want to go and look at some background. For the first time ever, I need to issue a content warning on a math video. We're going to use as the context for our exploration a historical instance of a tremendous race-based miscarriage of justice. And probably this will be concerning to everyone who watches it. If you are someone who, for reasons of your own, has greater sensitivity, greater difficulty approaching topics of that kind, you should be warned ahead of time. In using Swain's story as a means of illustrating hypothesis testing, it's not my intention in any way to trivialize it or to make frivolous use of it. My hope is first to be able to tell his story so that more people are aware of what went on, and also to illustrate the power of math to shine a light on important and sometimes troubling situations. The story involves a man named Robert Swain, who was accused, tried, and convicted of assaulting a white woman. He was a black defendant. This was in the mid-1960s in Alabama, Talladega County, Alabama. In Talladega County at the time, there were about 16,000 eligible jurors, about 26% of whom were African American. There was a jury pool of 100 from which the jury itself for his trial was to have been drawn. And in that jury pool, there were 8 African American jurors. If you know anything about criminal trials, you know that there's a process called voir dire, in which prospective jurors are questioned by the court and by the counsel for the parties to try to determine whether there's any obvious bias or conflict of interest that would prevent them from serving in a disinterested manner on the jury. And the court can strike potential jurors for cause. And typically, depending on jurisdiction, there's some number of what are called peremptory challenges that are allotted to the parties. So you don't have to give a reason. You can just say, I don't really like the look of that juror. I don't think it's going to be good for my side of the case. I'm going to strike that person. And all 8 of the African Americans in this jury pool of 100 were struck for one reason or another. 6 of them were struck based on peremptory challenges. So Swain was convicted. I have no idea whether he was guilty, but he was convicted by an all-white jury. And he appealed. And his argument was that African American residents of the county were systematically debarred from serving on juries. It was historically the case that since 1950, I believe, and this case was in the mid-1960s, since 1950, no black juror had actually served on a criminal trial jury. And the jury panels from which the jurors were chosen tended to be about 10 to 15% African American routinely in a county where the actual representation was 26%. So the basis of Swain's appeal was African American jurors are not being allowed into jury pools in proportion to their numbers in the county. And once they're in the pools, they're just not getting on juries. And I was not judged by a jury of my peers. There's a 14th Amendment issue. We're going to focus in this video on one aspect of that selection process, and that is the question, how likely is it that in a county that's 26% African American, a jury pool of 100 would only contain 8 African American potential jurors? This is, if you know something about probability, a case of a hypergeometric distribution. So We reach into the pool of 16,000 potential jurors. We grab one, we place them in the pool. That slightly alters the probability that the next person that we reach in and pick will be either a white juror, an African American juror, or whatever other identifications people might have been making in that time and place. So we should, I suppose, strictly speaking, take that approach. But this is very, very, very close to being a binomial distribution, because if you reach in and pick 100 people out of a group of 16,000, the actual alterations that you're going to make in the likelihoods from one selection of one person to another is going to be negligible. So for our purposes, we reach into this population, we get a fixed number of people. They have essentially a fixed probability of being African American. Presumably it's independent. That's a thing we want to test, right? Is the race of the juror independent or not from one pick to the next? And so we have all the conditions for a binomial distribution. You'll see on the screen the relevant binomial distribution. So this is for n equals 100 and p equals 0.26. So what you're looking at is the probability distribution for the number of African American jurors you would expect to see in this jury. And unsurprisingly, it's centered at 26. If 26% of the population is African American, you would expect on average to get 26 African American jurors out of a given 100 in a random process. And then, but you wouldn't be shocked if it were 20, you wouldn't be shocked if it were 30. By the time you get out to down around 12 or so, or up around 40 or so, things start to feel awfully unlikely. And you'll recall it was 8 in the case of Swain's panel. I've highlighted down in the corner the area from 0 to 8. So if we ask ourselves the question, what's the likelihood of being at least as far away from expectation as 8? The answer is visually, well, we'd be over there. And as you can see, the probability is negligible. And in fact, if you perform the calculation, you find that the probability of having 8 or fewer African American jurors under these conditions, if the process were fair or random, is 0.0000005. It's tiny. It's just tiny. It beggars the imagination that this process was actually random, particularly since it seems to have been repeated to some extent or another, time after time after time after time after time, across many trials in this jurisdiction over many years. So the logic of our argument was sort of, let's see what things ought to look like under the assumption that things are fair. Let's compare that to what was actually seen, and let's draw some sort of conclusion. You'll see on your screen a description, a formal description of this process that we're going to call hypothesis testing. And it begins with the framing of 2 statements, a null and alternative hypothesis. A null hypothesis is a statement that says there's nothing going on. If you're testing the fairness of a coin, the null is that the coin is fair. If you're testing for differences between groups, the null is that there is no difference. If you're testing for some sort of dependence between quantities, the null is that there is no dependence. If you're testing for whether a process seems to have been random or not, the null is that it was random. So it's always a statement that there's nothing going on. That's contrasted with an alternative hypothesis, which often is the logical complement of the null. It doesn't have to be, though, for the following reason. It may be the case that a deviation from expectation in one direction is reasonable to investigate, and in another direction is not. And the case of Swain is a good example of that. You would not really need an alternative hypothesis that says, well, maybe also Black jurors could be overrepresented in the 60s in some Alabama county. That's just not reasonable. So sometimes it's not the logical complement. Sometimes it's what's called a one-sided alternative versus a two-sided alternative. But anyway, you have your alternative hypothesis. Your next step is to choose what's called a significance level. And a significance level is basically sort of a cutoff value. So you'll recall that what we did was we calculated the probability of seeing 8 or fewer jurors in a randomly selected pool of 100 from this county, and we found out that it was incredibly tiny. So that incredibly tiny probability causes us to strongly doubt the fairness of the process, the randomness of the process. On the other hand, if that probability had been relatively high, we might not be very concerned at all. And so there's some cutoff between, yeah, this is too low. I just don't believe this was fair. And no, this isn't so bad. I'm not gonna get all excited about there having been some sort of hanky-panky. The boundary between I'm probably okay with this and no, I'm not okay with this is called a significance level. It tends to be a smallish number. 0.05 is quite often used. 0.01 and 0.1 are fairly often used as well. The next thing we do is to calculate what's called a p-value. And our p-value was 0.000005. It's the probability of seeing a result at least as extreme as the one that was observed if the null hypothesis were true. This is called a p-value. And you'll see on your screen a little sort of gauge I made to kind of indicate how to understand p-values. The p-value is not the probability that the null is true, but it is a gauge of our confidence in the null. So if your p-value is pretty high, close to 1, we should have no issues with the null, because the thing that we observed is quite likely if the null is true. If the p-value is quite low, we tend to strongly doubt the null, because the thing that we're seeing is not likely under the assumption that the null is true. And finally, we compare the p-value to the significance level. And if the p-value is below the significance level, we reject the null. We don't have enough confidence in the null to commit ourselves to believing it to be true. If the direction is reversed, if the p-value is above the significance level, then we don't reject the null. What we say is we don't have enough evidence to reject the null. It was common once upon a time to say that the null was accepted, and for reasons that you might imagine, that nomenclature is sort of gone out of fashion. If we reframe the Swain discussion more formally, it looks like what you see on your screen. The null would be that the jury selection process was random, and numerically that would mean that the probability of an African-American citizen of the county being in this jury pool was 0.26. The realistic alternative is that the probability is less than 0.26. So we would want a one-sided test here, because it's not credible to imagine that there was a bias in the other direction in that time and place. The significance level often is represented with a lowercase Greek alpha, so I chose 0.05 just because it's very commonly used. And then you'll see there the calculation of the p-value. You don't need to sweat the details of that if you're unfamiliar with binomial probabilities. But it's clearly extremely tiny, orders of magnitude below the significance level. And so our conclusion would be that we should reject the null hypothesis. We should say something about errors, because unlike much of the rest of the math with which you are familiar, it's possible for the result of a hypothesis test to, in some sense, be wrong. And this is a bit of a departure, right? If you think about geometry, you have a right triangle with sides of lengths 3 and 4, then the hypotenuse has just got to be 5, period, end of discussion. That is a cosmic certainty. But in the case of this testing process, one can get a wrong result, and you'll see a little table on the screen that sort of describes how that works. If the null is true and you fail to reject it, everything's good. If the null is false and your test does cause you to reject it, everything's good. If the null is true, there's some small chance you might end up rejecting it anyway, right? There is some teeny tiny probability that in the Swain jury pool, we could have seen a result this extreme. It's so tiny, it's just unbelievable, but it's non-zero, right? So errors of that type are called type 1 errors. If a null is false and it's not rejected, that's called a type 2 error. There are things that you can say about the likelihood of a type 1 error or a type 2 error in a given situation that's beyond the scope of our video. But just recognize that, unfortunately, you can never know whether you actually have a type 1 or a type 2 error going on in your particular test. So unfortunately, the Supreme Court ruled 6-3 against Swain. They seem to have focused on the peremptory challenge process, and they seem to have made a very naive comparison of the 26% African American population in the county and the 10 to 15% representation repeatedly in jury pools. And they said to themselves, well, it's only a difference of 10%, and that's not that big a deal, which, in my opinion, shows a profound misunderstanding of the probabilities involved in these situations, and a sort of disinterest and indifference to the situations that were faced by these defendants. And so also, unfortunately, Swain was executed. In the 80s, this case was decided in 1965. In the 80s, I believe 1986, there was a case that reversed much of the thinking in the Swain case. And it's a little bit easier for defendants to come into federal court and make the argument that they have been treated unfairly by means of the racial representation in their juries. So it's a bit of a downer, the context, but I think it's an important context. And I hope it serves to illustrate the potentially tremendous importance of being able to make analyses of this kind. So go forward and use this knowledge for good, ethical mathing.